All right, so we're back. We're going to be doing an addition of three different vectors to find out what the resultant vector of something pulling in all three of those directions is. For this, maybe it'd be helpful to visualize something. So imagine three people, three lumberjacks pulling on a tree, and we want to know which direction the tree is going to fall. They're all pulling in different directions, and they all have, well, one of them has significantly less strength than the other two. So we have force B. This is one lumberjack pulling with 20 pounds going in this direction. We have force C, which is pulling with 85 pounds. This lumberjack's way stronger, pulling in 30 degrees down from horizontal. And then 80 degrees down from horizontal is another lumberjack capable of pulling 85 degrees. And we want to know where that tree is going to fall. And I've just drawn in an approximation here. An approximation, if you look at that and if you think about it, you can you already know trigonometry. You already all know trigonometry. You're going to say, like, it's going to fall somewhere in here. We've got two people pulling 85 pounds, like that direction, so it's going to be somewhere in between here and this weakling that's pulling 20 pounds. They're going to barely affect it, but it is going to push it closer to C. And that's kind of what I've approximated in drawing this, right? And if you do an approximation like this when you're setting up a problem, just based off of your gut feeling of where it is, you'll be able to kind of see what you need to do. It'll help you set up the problem, and it'll help you think things through. Here's the thing. Right now they're all going in different directions, and so we don't have a common frame of reference for them. So in order to add these together, we need to create apples and oranges, and we need to add all the apples together and add all the oranges together in order to get the f of y and the f of x of our component, of our resultant. So what I've done here is I've already pre-done this up so that you don't spend a lot of time watching me write stuff down. We have the a of x. So this is a right here. And we're looking at the x direction here. And we've got our 80 degrees here. So that is the adjacent over the hypotenuse. The hypotenuse is 85. So what we use is cosine, adjacent, ca. So 85 cosine 80 for the x component, and that's just this there. And then we're going to take the next x component, which will be c, and we're going to add that there. And then we're going to add the next x component, and we're going to add that there, and we're going to see the total x component on here, which will be above this.
Yep.
So let's do that real quickly here. So 85 cosine 80 equals, Mike, can you help me out?
Yes. After some quick math, we have 14.76.
14.76. And these are all in pounds.
These are all in pounds.
Okay.
And then if we're looking at our next one, so bx 20 cosine 30, we're at 17.32 pounds.
17.32 pounds.
And then for cx, we have 85 cosine 30. That's going to be 73.61 pounds.
73.61 pounds. And we add all those up.
We're adding all of those together. We have a grand total of 105.69 pounds.
105.69
pounds.
Okay. So what we've gotten real quickly there, and it's just doing repetitively the same thing, and that's what happens a lot when we're doing statics calculations, is really repetitive things. We're just finding the same equation over and over with different angles and using different things. It's important that you keep things together, and it's important that you mind your signs, as we'll see here in a second. So 105 pounds, if we look, that's just all of these three numbers added up there. And if we go over here and we draw something that looks like 105 pounds, it's going to be like right here. That's 105. And that is our x component of this resultant. And I drew this like not quite as long as it needs to be.
Yeah. so we just modify that.
Modify this a little bit. I'm adjusting my expectations,
Yeah.
right? So we've got our f of x of 105.69 and 0.69. Now over here, when we're doing the f of y, we're using sine on this one because we're all operating off of the same ones, but there are two negative ones. B is in the positive direction, is in the positive quadrant, and then C and A are in the negative. So when we start with the A one, we put a negative in parentheses around what we would normally calculate here.
Right.
This is just keeping the sign straight so that we know which direction it's going. So the A of y is minus 85 sine 80. So 85 sine 80 is what?
We got 83.71, so that's going to be negative 83.71.
83.71. So it's minus 83.71. 20 times sine 30, and this one's positive.
Yep. And that's going to be 10 exactly.
It's going to be 10. Okay, and all of these are pounds.
Yep, those are all pounds. That
Pounds.
one's positive 10.
And that's positive 10. And this
Yep.
one is negative 85 sine 30.
That's going to be negative 42.5.
42.5. Interesting thing when you're dealing with 30 degrees and 60 degrees, you know, like the sine of 30 degrees equals 0.5. The cosine of 60 degrees equals 0.5. So it makes some of the math a lot easier when you're dealing with 30 degree and 60 degree angle triangles.
Yeah, if you just remember that your sine and cosine for those complementary angles are going to be 0.5.
Yeah.
It simplifies the math quite a bit.
Yeah. So it's always nice when you got a 30 degree or 60 degree angle. It makes things super easy.
Yeah.
They're magic triangles. Let's go ahead and look then at what this adds up to be. So we're going to have 10 minus 83.71 minus 42.5.
I'm just catching up on my calculator here real quick. So we have 10 minus 83.71 minus 42.5. That's going to be minus 116.21.
So, and that's our f of y, and that's going to be down here, right?
Yep.
And that's going to be minus 116.21.
And that should be a little bit farther down than our 85.
Yeah, it should be like down here.
Yeah.
I think that's about right.
We're getting there. Yep.
116.21.
I think one thing to keep in mind when you're doing these is that if we have a protractor that gives us like our exact angles, and we can use a scaled value for a linear distance, like we can, if we know the scale of this, we can draw these in a way that they exactly match these.
If we did this in CAD,
Yes,
it would work.
This would work perfectly.
Except for it doesn't really accept pounds as a
It doesn't
unit.
accept pounds as a valid variable for
a distance.
For a distance, but if you correlate a linear distance in CAD to the magnitude here, all of this math would work out perfectly. The angles would be exact.
Yep.
The linear distances would be exact.
So now all we need to do is we just need to find this angle of theta. Right there of our resultant, because we've got our magnitude. Or no, we need to find our magnitude and that,
Yeah,
right?
we still need our magnitude.
We still need our magnitude. So that magnitude, all we need to do there is a squared plus b squared equals c squared. So that is going to be the square root. So our magnitude is going to be the square root of 105.69
0.69
squared plus
The
116. And once we square it, it's going to be positive
It's going to be
anyways.
positive anyways. So
So 0.21 squared, and that equals a really large number on both sides.
yep, this is where you use your calculator.
This is where you use your calculator, and you're going to come up with that actually equals out to.
Want to double check my math here. That's going to be 157.08 pounds.
Okay, say that again.
157.08
157.08 pounds. So that's what this length is here, 157.08 pounds. And so clearly I draw this even longer.
Yeah.
I didn't get this to scale, but it's okay. As long as we get this labeled right, everything is okay. We kind of got the direction right. So let's look here and see. Now we've got that length right there, our hypotenuse here. And we can now use tangent to the -1 to figure out what theta is. So if we use tan to the -1 of,
So if
we're talking about opposite, which is 116.21
over,
over 105.69.
yep.
Those are,
Let's do our quick math here. Our angle comes out to be negative 47.71.
negative 47.71.
71.
And when we look, our approximation got really good at the angle. The length it didn't do as well at, but our approximation did really good at the angle because this looks like 47 degrees. That looks slightly off of 45.
Yeah.
So there we go. And then this is also like when you're setting up these problems, don't let them be not tied to reality, right? If you have to make up lumberjacks, make up lumberjacks. Do whatever you need to do to make it work in your head as an analogy, because we were able to kind of draw pretty close to the right line here without doing any math.
And we were like, if you think about this, if we tie this to like a practical thing, it's like we were kind of guesstimating where like this theoretical tree would fall, like what line it would fall on if we were applying these forces to it, right? And we got pretty close. Humans in general have a pretty good intuitive understanding of how these relationships work together in real life.
Yeah.
Your gut sense is probably going to be fairly close. I would say probably 80 to 90% of the time.
Yeah, and I know it's hard for a lot of you to trust your gut when it comes to mathematics. You should be trusting your gut over your fear of mathematics, because we just proved our gut through mathematics. That's really what, like, that's how math was invented in the first place.
Yeah, and the this is something that people have an intuitive understanding of. It's kind of ingrained into how we navigate a three-dimensional space and how we estimate the relationships between objects that are near and far from each other. So, like if you're thinking about a problem and you have a gut sense that the line is going to fall under a certain place, start with that assumption and build the problem around there.
Yeah.
Because you will find that the majority of the time you were fairly close from the beginning.
Absolutely. And, like, we took a complex problem here.
Yeah.
And we broke it down into a bunch of simple problems.
Yeah.
This is the systems approach, just period.
Yeah.
Right?
Yeah.
We're just systems approaching this. And that's what we're doing with this math. Is like we're just adding up like simple problems to equal a more complex problem. The rest of statics doesn't really get much more complex. It gets more complex. It just doesn't get any more difficult. Yeah.
Like the math does not get more difficult than beyond what we've essentially done here.
Yeah, like the math, we've already set up the extent and depth of math that we're going to do.
For all of statics.
For all of statics. It's just a matter of you got to keep track of a lot more.
Yeah.
The more complex a problem gets.
And we could add yet a third dimension to this. We've plotted this on 2 dimensions.
Yeah.
If we needed to add a third dimension here, we would just do one more cycle of this, and it would be a of z B of Z, C of Z, etc. And that would,
Yeah, like maybe this lumberjack that's only pulling 20 pounds,
yeah,
he's actually just as strong as this person is here that's pulling 85 pounds. It's just that the rope that he's holding onto is way further up the tree.
yeah,
And so therefore in this plane, it's only 20 pounds. But if we take a Z height, it's something else.
yeah,
So then we would have to scale that in each of the planes in order and then add things up, and we would get a full three-dimensional thing. We would basically tripling our work as far as the number of calculations are
we do.
concerned, because you'd have to figure it out in each of the planes.
but you can do it, like the math doesn't change.
The math does not change.
So, and we did it in 2 dimensions here because representing 3-dimensional planes on a whiteboard like this gets more
Sucks.
it gets more complex.
We'd have to erase this and do the YZ plane, and we'd have to erase that and then do the
Yeah.
XZ plane. And then we would add all of those numbers together. But none of that would get more difficult as far as the math is concerned. It's just repetitive.
Yeah, it gets repetitive and tedious. So we kept it to 2 planes here.
Yeah.
And if you guys do a lot of 3-dimensional stuff related to this, you're going to use CAD software 9 times out of 10 to solve these problems.
Absolutely. So those are our 3 problems that we wanted to give you some practice with. You can, in actuality, on the slide shown there, if you count up the squares, it doesn't actually work out to be exactly what it is as far as the directions are concerned. Those angles are not right. It's not 30 degrees. It's not. I did that because 30 degrees makes math simpler. It's something more like in the 32 or 34 degrees range. But you can figure that out by counting out those squares. So one thing that you could do is you could redo this problem, get some more practice using this slide, and then figuring out what those actual angles are besides the 80-degree angle. The 80-degree angle is written down there, but the 2 30-degree angles, those are inaccurate for how it's drawn to scale using the grid there. You can use the grid to figure out what that angle is by just counting the lengths of the sides and using, inverse tangent to find that theta.
Yeah.
So that's a good way for you to use this to get some additional practice on it. And we will also provide you with additional practice problems if you want to dive in and get more practice with this.
Yeah. So I think that wraps up everything on this problem and the topic for today.
On the topic of vector addition, we did all of the we came up with the scalars from a resultant. We came up with the resultant from scalars, and then we added 3 different vectors together using the scalar components to find the resultant of those 3 separate ones.
Yeah.
So there we go. We'll see y'all next time.